Hello students, in today's class we'll continue and we will read about resistivity of various materials. So see, our materials in a periodic table are classified into three different classes such as conductors. Like when we are talking about electrical current and how that current is been flowing, then we do not consider metals, non-metals and metalloids. We consider conductors, semiconductor and insulators. We have seen that these easily allow flow of current, whereas it depends upon the condition. In case of semiconductor, depends upon the condition in which semiconductor is, and insulators are the slowmost, or they provide resistance, or we can say hurdle to the flow of current, provides hurdle to flow of current. So why is it happening? It happens due to their conductivity or their property to conduct the electric charges. And here if we see, the conductivity of conductor is very high. Conductivity is high. Medium. For semiconductor it is medium. It's neither high nor low. It depends upon the condition. If the optimum conditions are provided, semiconductors will show a good conductivity, and in case the conditions provided aren't optimum, then they will not show any conductivity, and in case of insulator the conductivity is low. The other concept, which is the other face of the coin of conductivity, is the resistivity. So for conductors, resistivity is low. Resistivity is ability to resistance or ability to provide the resistance to the flow of electric charges. So it is low. It's medium for these semiconductor materials, and it is high in case of insulators. It is high, that's why flow of current is obstructed. Okay, now we will understand what is the definition of conductivity. So, our conductivity is defined as an intrinsic property and it's the measure of amount of electrical current a material can carry. Measure of amount of electrical current a material can carry. Okay, now this is also known as specific conductance. Too known as, this is very much important for us to know specific conductance. And its SI unit is Siemens per meter. I'll expand it. Siemens per meter. It is also defined as the ratio of current density to the electrical field strength, denoted by sigma, and defined as ratio of the current density to the electric field strength. So now let's move on and let's understand how much conductors provide conductivity, semiconductors provide conductivity, and insulators provide conductivity. So resistivity of various material. Materials are classified as conductors, insulators, and semiconductors based on their resistivity. It's based on their property of providing resistance to a particular motion of electric charges. The resistivity, which is denoted by a symbol called rho, for metal, its value is 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. Ohm meter is the SI unit of our resistivity. And for insulator, it is 10 to the power 18 times greater than the metal. Resistivity rho for insulator is higher for when compared to the rho for metal. By what factor? Rho of insulator equals to 10 to the power 18 into rho of metals. This is the relation between resistivity of insulator and resistivity of metals. Now semiconductors. They have resistivity characteristically decreasing with rise in temperature. Here rho is inversely proportional to the temperature. As the temperature increases, the rho is decreasing. Okay, so a semiconductor, if we take silicon, it will show higher resistivity when the temperature is less. If temperature is increased, it will show resistance which is lesser, and the flow of charges will be more. Flow of charges more. So here what exactly it states that in case we want semiconductors to behave like conductors, we need to provide them the required or suitable temperature. Resistivity of semiconductors can be decreased by adding small amount of suitable impurity also. Increasing the resistivity implies increasing the conductivity. Now semiconductors. In this semiconductors, there are two factors. One is temperature and another one is impurities. Just remember, if we are increasing either the temperature or the impurity, we are increasing its conductivity or we are decreasing its resistivity. So this is the relation of semiconductors to the temperature, to the impurity with respect to its conductivity and its resistivity. Now let's say a little about the resistivity. I'll give you the brief. What is resistivity? So resistivity is denoted by rho, and we can equate resistivity as electric field upon J. J is the current density. J is the current density. Next to it, again rho can be given as R A upon L, where R is the resistance, A is the area, and L is the length. Now in CGS units, it is written as ohm per ohm centimeter, and SI unit it is written as ohm meter. Its dimensional formula is M1 L cube T to the power minus 3 and A minus 2. This is very much important with respect to your entrance examination. Then factors determining resistivity, R. A is nature of material, whether it's a conductor, a semiconductor, or a insulator. Then B is temperature. Temperature, if increased, resistivity will decrease. If temperature decrease, resistivity will increase. Okay. Now I will give you few additional information. That is numeral value of few important elements. So we have seen that for us, they say that gold and platinum and silver are inert metals. So what about their resistivity? That's so we will see their particular resistivity. For silver, it is 1.59 into 10 to the power minus 8 ohm meter. Then for platinum, it is 10.6 into 10 to the power minus 8 ohm meter. See the range, it is all 10 to the power minus 8. So these are inert metal. Now one more inert matter, like it's not exactly the inert matter, but it have higher temperature dependence, that is tungsten. Tungsten, it melts at a very high temperature of 3400 kelvins. So its resistivity is 5.6 into 10 to the power minus 8 ohm meter. Then we have like copper. These are usually we use copper, iron, where in our electrical connections we say that these have good resistivity, good conductivity. So what is their resistivity? For copper, it is 1.68 into 10 to the power minus 8 ohm meter, and for iron it is 9.71 into 10 to the power minus 8 ohm meter. Now we'll see about the mercury. For mercury, it is 98 into 10 to the power minus 8 ohm meter. Next to it is our nichrome. What is nichrome? In the previous slide you can see nichrome is an alloy, and this alloy have nickel, iron and chromium as component. So its resistivity is 100 into 10 to the power minus 8 ohm meter. Now I'll give you resistivity value for few our insulators. So first of all, carbon, graphite. Carbon in the form of graphite. So these are insulators which are written in the blue. So for it is 3 to 60 into 10 to the power 5 ohm meter. See the range, it comes into plus 5. Here we have seen minus 8. Now second is our glass. Glass is also an insulator having resistivity 1 to 10,000 into 10 to the power 9. Then quartz having a resistivity of 7.5 into 10 to the power 17 ohm. And fourth one, or the last one, I'll say hard rubber. It's having a resistivity of 1 in the range of 1 to 100 into 10 to the power 13. 10 to the power 13. So these are the resistivity value for few conductors and few insulator. For your reference, for you to understand properly how the range is being defined. If I say this is a range plot, here is the 10 to the power minus 8 ohm, and here is the 10 to the power 13 or 17 ohm. So on this particular scale, you can say that this belongs to conductors, this belongs to insulators, and in between will come the semiconductors. Okay. So this is all for today's class. I hope you understand the concept of resistivity and conductivity, their symbol and their CGS unit and SI unit along with their dimensional formula, and factors which determine the resistivity or which affects the resistivity, and along with the range in which they are. The range of resistivity for conductors and insulator is quite an important factor which will be asked to you in various entrance examinations. Okay, so prepare well. This is all for today's class. We'll meet in the next class. Have a good day. Bye bye.